Hello, my name is Miha Kirila. I'm a computer science PhD student at the University of California, Irvine, and today I'll be presenting my research. The work titled A Heterogeneous Solution to the All-Pair Shortest Path Problem using FPGAs has been done in collaboration with my colleagues and advisors from the Department of Computer Science and with the help of Xilinx. In this presentation, I am going to cover the problem we've tackled, our proposed solution, the implementation of our solution, as well as our results and conclusion. The all-pair shortest path problem is a pretty common problem in the field of graph theory, and it's used for analyzing the paths in various graphs, and used for computer networks, social networks, databases, etc. The problem itself involves finding the shortest path from every vertex to every other vertex in the graph. The most common algorithms used for solving this problem are Floyd-Warshall, Bellman-Ford, or using Dijkstra for every vertex in the graph. All of these algorithms share a common problem, that is, they are very sequential, and any implementation will not be able to exploit hardware parallelism. Therefore, we propose a heterogeneous solution that involves using a CPU-FPGA system and using a hybrid Floyd-Warshall Matrix-Multiply algorithm to exploit hardware parallelism. We've chosen the Kleene algorithm because it has allowed us to replace most of the sequential computation with multiple matrix multiplications, which can be done in a highly parallel fashion. In the recursive version of Kleene's algorithm, we recursively decompose the adjacency matrix of the graph over the main diagonal, as shown in the figure. And once we are on the lowest level of recursion, we call Floyd-Warshall on the blocks that are on the main diagonal, the ones that are grayed out. So we will call Floyd-Warshall on block A, and then use matrix multiplication operations to update all the adjacent blocks. Once block D is updated, then we call Floyd-Warshall on that block again. And then we perform the reverse operation. So we update the adjacent blocks on the same level, B, C, and A, using matrix multiplication. And now we have a computed block that will become a new block A on the upper level. And then we repeat this operation recursively. And this way we are trading off a highly sequential operation like a Floyd-Warshall for multiple matrix multiplication calls on the same data. And this can result in a faster execution time due to the highly parallel nature of the matrix multiply operation. However, in order to make all of this possible, we need to make some changes to the algebra we are using. And that is because Kleene's algorithm was originally designed to solve the transitive closure problem. And so we need to define our all pair shortest path problem as a transitive closure problem. That means changing the algebra to a closed semi-ring, and this implies changing all the multiplication operations to additions and all the additions to minimizing operations. In the upcoming part, I will cover the architecture of our implementation and go into further details of how the matrix multiplication and Floyd-Warshall kernels have been implemented. For our heterogeneous platform, we decided to choose a typical host device scheme, where our host handles the usual host operations, such as setting up the device and loading all the necessary data onto it. In this case, the adjacency matrix of our graph. And in addition, it needs to perform all of the Kleene computation to generate the instructions for each of the kernels on the device. The device itself hosts 3 kernels, which take turns in accessing the device's memory to load blocks of the adjacency matrix onto each kernel, update the data on it, and then store it back onto the device memory. The reason we choose 2 matrix multiplication kernels is because we noticed we can exploit parallelism in the updating phase of the Kleene algorithm. So we noticed that some matrix multiply operations can be done in parallel, and therefore we've reduced the number of matrix multiply operations between each Floyd-Warshall call from 6 to 4. While looking at our device's resource utilization graph, we've noticed that even on an older FPGA like ours, the amount of utilized resources is less than half, which opens up the possibility of running multiple instances on an FPGA, which can be useful, for example, for a data center application. For our matrix multiply kernel, we've used Xilinx's own general matrix multiply library. The kernel in this library uses a systolic array to stream the input matrices and compute the result of the matrix multiply operation in a highly efficient manner. To adapt this kernel to our own algorithm, we have to make some changes, such as eliminating the instruction encoder and integrating the GEMX engine straight into our algorithm, and also modifying the algebra to perform the correct operations. For our Floyd-Warshall kernel, you can notice that the naive implementation is highly sequential and does not allow for any sort of hardware parallelism. So before we can accelerate it, we need to make some changes to the algorithm itself. In order to exploit parallelism and bypass the data access conflicts of the sequential algorithm, we've split it into stages. And in each stage, we exploit pipelining and loop unrolling as much as possible. Depending on the Floyd-Warshall input size, which needs to be determined beforehand, we define an appropriate number of processing elements, which coincides to the number of row or columns in our computation. And then each row and column in the first stage will be streamed alternatively through the processing elements, such as each row or and column K reaches processing element K. Along the way, in each processing element, each row and column will get updated against the existing rows and columns in those respective processing elements. After each row and column has reached its designated processing element, we can move on to the second stage, where we select the rows or the columns. It doesn't really matter which ones, and we stream them starting from processing element 0. We stream them through the entire pipeline. And as each row, for example, gets streamed through the subsequent processing elements, it gets updated again. And when it reaches the end of the pipeline, it will be holding the final result. For our benchmarking section, we've tried to match the algorithms and the hardware as best as we could. And where that was not possible, we've tried to use metrics that would provide as relevant of a picture as we could. For our implementation, we've used a Xilinx FPGA Accelerator card connected to a Core i7 host. Whereas for the GPU benchmarks, we used a Titan X Pascal, which is designed on a 16 nanometer process node. The CPU benchmark, we've used the best results for the highly vectorized or partially vectorized Floyd-Warshall implementation, whichever performed best for each of our input sizes. This benchmark was performed on a 6th generation Intel Xeon processor. When it comes to the existing state-of-the-art in terms of FPGA computation of this problem, we had to make some concessions. That is because the existing work is very old, and the existing results could not easily be scaled to current technology. And therefore, we decided to use a different metric for our comparison, and that metric is the ratio of performance gained compared to a basic 32 by 32 computation. This shows us how well the algorithms scale with input size. We can see that the state-of-the-art algorithm scales very poorly with input size, whereas our implementation, due to the matrix multiplication kernels, scale very well up to a large input size where the matrix kernel becomes saturated. When it comes to modern day benchmarks, we can see some interesting things happening. We noticed that for our implementation, for small input sizes, the performance is relatively bad. It's very close to a CPU implementation, and that is because due to the small size of the input, the pipelines don't get exploited. As we go up in input size, we notice that our FPGA performs better and better, and it closes the gap to the state-of-the-art GPU implementation. In the last part of this section, we're going to take a look at the power draw and power efficiency results. All the GPU's performance comes with a drawback. It's high power consumption, even when compared to a 16-core CPU. Even though it has this high power consumption, overall, the GPU with its speed can still perform more operations per watt. However, there is a huge difference in the node process between the GPU and the FPGA we've used. The GPU is using a 16 nanometer process, whereas the FPGA we used is on a 28 nanometer process. If we are to scale that performance based on process node advancements, we can see that the performance of the FPGA can, at least in theory, match or surpass the GPU's performance, and the power usage is even lower than before. This, we think, can be a valid comparison because most FPGA designs are made to eventually be cast on an ASIC, and for that you would be using generally the most advanced process node available. Based on the results from our comparisons and from our data from our implementation, we can reach some pretty interesting conclusions. Due to the heterogeneous nature of our system, we are able to take advantage of both the CPU and FPGA's architecture to surpass previous FPGA implementations and compete with existing GPU solutions in terms of performance per watt. This ultimately opens the path to implementations in data center applications or even low power applications for IoT or mobile systems using ASIC designs. Thank you everyone for your attention, and if you have any questions, please feel free to contact me at the email address listed on the slide. Thank you very much and have a good day.